linear algebra. In this lecture we shall go through some examples of vector spaces. Our first example is the zero vector. First of all, how do we know it's a vector space? Well, think about it. It's a set which satisfies both the vector addition and scalar multiplication properties of a vector space. Well, what are these? Well, vector addition says that u plus v is in V, given that u and v are in V. But of course, the only vector is 0, and therefore vector addition does hold as 0 plus 0 is equal to 0, which is in V. Okay? The second is that scalar multiplication holds. What does that say? It says alpha V is in V. Remember, both these are given that V and u and v are in V also. Again, only vector is 0, and therefore it is true that scalar multiplication holds. Because alpha is 0 is equal to 0. Just so it's clear, the underlining of the zeros refers to the fact that 0 is a vector. To be consistent, v is a vector also, u and v are vectors also. This is called a trivial vector space. The vector space is 0. Why? Well, because it's not that interesting. Okay, moving on to a more interesting vector space, and one that will be a primary focus for us in this course is the real vector space. Why is it called real? Real refers to the fact that the elements of the vectors are all real numbers. So if we have a vector space each of these is a real number. Why? Because it's called a real vector space. We also know the number of the elements. Here there are n elements. Refers to the dimension of the real vector space here. So what all this nomenclature means is that each of the elements in the vector is real. That's all it means. So to give you an example, R7 refers to a vector with this number of elements. There are 7 elements in the vector, hence it's in R7. Each of these elements is real, hence why it's a real vector space. The funny looking R is a way of saying real.
So
to give you some intuition about what we're doing here, when we talked about the third floor of the block of flats, that would be a real vector space in R squared. So area relates to R squared. Examples might be minus 3.785 or 0, 0. The key thing that makes this vector part of R squared is the fact there were two real numbers. So each element, there were two elements, both of them are real numbers. A line refers to a real vector space R1, and examples could include so these are vectors, or finally real vector space R3. Examples could be now all these vectors are just arbitrarily chosen, but they're to illustrate to you what vectors in each of these vector spaces might look like. Of course, there's no reason to stop at R3, and we regularly work with vector spaces in R4 and above. Now, what are all these elements? The elements in these vectors, they're all just real numbers. Hence why it's called a real vector space. Now, what's the intuition here? The intuition is that all these numbers can be plotted on a number line, right? E.g. pi is roughly 3.14, or minus 3 over 2 is here on the number line, or 1.768 is roughly here. They all exist on the real number line. So the key thing to realize here about real vector spaces is that the coordinates of points in the real vector space are real numbers. E.g. the real vector space R3 has 3 axes, 1, 2, 3, and it has real numbers along those axes.